Hello, I'm Matthew Reiss from Queen Mary University of London, and in this video I will present our work on general purpose audio effect removal for WASPAA 2023. First, some background. Audio effects are natural or synthetic manipulations of audio recordings and are ubiquitous tools in modern audio and music production. Some examples include reverb, delay, noise, and distortion. Often, multiple effects are combined, as seen in this guitar pedal example. Sometimes we would like to change or remove existing audio effects. This can be achieved by an effects removal model trained to analyze the affected audio and remove the effects it finds. Applications include cleaning up noisy or distorted speech and music recordings, or further enhancing the remixability of outputs of audio source separation models, which today can isolate instruments but cannot remove present audio effects. Previous works have attempted to tackle this problem, but tend to focus on removing one type of effect from a single source. For example, removing distortion from electric guitar, reverb from vocal signals, or different types of corruptions from speech. In this work, we introduce a new task to focus on a more general case, which we entitled General Purpose Audio Effect Removal. We first experiment with 5 existing architectures across both single and multiple effect removal tasks. Finally, we propose RemFX with FXAug, a compositional approach that outperforms our baselines. Here is an audio demo of our final system. This is a short guitar clip with reverb, chorus, and dynamic range compressor present. This next clip is after that first clip is passed through RemFX, which attempts to remove all 3 of these effects. In general purpose audio effect removal, we first define a set of n functions f1 through fn that represent a group of common audio effects. For each audio example, we randomly sample the number of effects to apply, k, then randomly sample k effects from f without replacement. We then compose these effects in the order that they were drawn in sample parameters, then pass our input through the effects chain. Our goal is to construct a function g that will estimate a recording of our original x, minimizing some loss function. One idea to achieve this goal would be to implement what we call a monolithic network. In this case, we would train a single architecture to remove all the effects that it sees. However, we hypothesize that this may not perform well. Firstly, the combinatorial nature of having a range of effects present in any order increases the number of problems that the network has to understand. Secondly, because the number of effects applied and their parameters can vary significantly between examples, the model may focus only on optimizing the hardest examples with the most effects. We thus propose a different compositional approach which we call RemFX. First, we simply train an effect-specific removal model that is optimized to remove a single effect. Next, we train an audio effect detection model that can determine which effects are present. At inference time, we first use the detector to determine which effects are present, then select the relevant effect-specific removal models to apply sequentially to produce the estimate. This approach has a few advantages. First, this reduces the average parameters of the overall system, since most of the time only a subset of the effect-specific models would be required. Second, more effects could be recognized and removed by a system without a full retraining, since we would just need to add a new effect-specific model for that effect. And third, we can take advantage of certain model architectures that work better for particular types of effects. All of the audio examples we train with come from existing dataset sources of differing source content. For each example in our dataset, we first selected which existing dataset to select from, then choose a random 5.5 second chunk. Then we would apply a random number of effects from pedalboard in a random order, each with randomized parameters. The randomized parameters were constrained to prevent unrealistic examples. We will now show the results of many experiments leading up to the full task, including effect-specific removal models, monolithic models, using effects augmentation, and audio effects detection. For our first experiment, we trained 5 different architectures: DPTNet, Open Unmix, DCUNet, TCN, and Hybrid Demux to remove a specific effect. We report their SISDR and multi-resolution STFT error over each effect, as well as their average for the same metrics. Our main conclusion is that no single model performed optimally for all effects. Hybrid Demux tends to perform well for distortion and compression, while DCUNet performs better for reverb, chorus, and delay. Next, we focus on comparing the performance of effect-specific models to a monolithic counterpart. For the monolithic models, we trained both Hybrid Demux and DCUNet with the dataset of examples with one effect from the effect set applied. We then compare their performance on examples with one specific effect to the effect-specific models from the previous experiment. This table shows the multi-resolution STFT improvement for each case, and it is clear that the effect-specific variants outperform their monolithic counterparts. Since the full task would include examples with many effects applied, we were concerned that our effect-specific models would not be robust enough to these unseen cases of extra effects. Therefore, we also trained effect-specific models to remove a single target effect from samples with distractor effects applied, and again compared them to the original effect-specific models. We call this approach FX-AUG. We found that in general, these effect-specific models with FX-AUG perform better not only on examples with distractor effects present, but also on examples where just a single effect was present. For our effects detector, we compared training linear layers on top of existing state-of-the-art audio classification models to training a PANS model from scratch and report the class-wise accuracy. We found that overall, training from scratch tends to work a bit better, with a small boost from adding spectral augment. We are now ready to evaluate our complete RemFX system on the full general-purpose audio effect removal task. We compared the performance of 4 monolithic models with 3 versions of our RemFX system. The monolithic models included DCUNet and 3 variants of Hybrid Demux models with different numbers of parameters. Meanwhile, RemFX Oracle is given the ground truth labels and ordering to select the appropriate effect-specific models, while RemFX All simply applies all effect-specific models in a random order for each example. RemFX Detect uses the detector to determine which effects to apply, and then applies them in a random order. For the case where the number of effects applied is 0, RemFX Oracle and Detect significantly outperform the monolithic models, since the monolithic models tend to corrupt the input, while the RemFX models tend to leave the inputs untouched. For the case where the number of effects is 1 or 2, the monolithic models perform better, but are still significantly beaten by RemFX Oracle and Detect. As the number of effects increases, the monolithic models slowly catch up, but at n equals 5, while the results may seem to indicate that the monolithic models are starting to perform better, it is clear from our listening results that no model performs well. It is also clear that the knowledge of which effects are present helps, as blindly applying the effect-specific models with RemFX All significantly underperforms RemFX Oracle and Detect. Many directions exist for future work. A simple improvement would be to include more types of effects and implementations, like VST plugins in the training examples with corresponding effect-specific models. Also, modifications could be made to the inference procedure to consider more complex routing schemes that are present in many music production tools. These changes would likely improve real-world generalization. Finally, due to the rise of diffusion probabilistic models, we hypothesized that generative models may perform better than the filtering models proposed, since they would be able to generate a clean estimate without artifacts, especially in more difficult cases. In summary, we proposed a new task, general-purpose audio effect removal, and investigated a few methods of solving it. While the results are promising, more work is needed to improve performance in difficult cases and generalization. We provide audio examples, code, datasets, and pre-trained models on our project page. Thanks for listening.